Hello, and welcome to another chemistry topic together as we continue to explore more about formulas and equations and things that show a chemical change. We're going to talk today about something called an ionic equation. Within today's topic, we're also going to talk about our pre-lab details for the next lab that you will do later this week. So go ahead and fill in whatever date that you are taking these notes, and your topic is ionic equations. Our essential questions for this lab or for this topic are: how do I write complete and net ionic equations? But then also, what are the details for our next video lab? So essential question one is really the question we're answering for today's notes, but then we are also doing the pre-lab. So if you need to review this video again before you do the lab later this week, just remember that today's notes also has the pre-lab. So let's talk about this thing called ionic equations. Let's get into it. Before we get into some other new stuff, there's some vocab words I want to clarify. We'll be using a lot. These are also words that you'll eventually use to explain the results of your next lab. The term soluble refers to something that either will dissolve or is able to dissolve or can dissolve in something else. So sugar in water would be a great example. If we describe something as insoluble, when we put in front of a word for the English language, that means it negates or opposite definition of the original word. So then this would be it will not dissolve or it cannot dissolve. So for example, a rock in water will not dissolve. So those are just some terms we use for the lab we're doing today. Related to insoluble then is that vocab word precipitate. Remember, that was one of our 5 signs of a chemical change. So seeing a precipitate, really what you're doing is you're creating an insoluble compound that doesn't dissolve in whatever liquid, usually water, that it's sitting in. So then let's just review that definition of precipitate. Precipitate is a solid that forms after mixing 2 ionic solutions. It is a sign of a chemical reaction, but remember, it's very specific. It has to start by mixing 2 ionic solutions. We know what that word means now, so I can be a little bit more specific defining this term, precipitate. So our lab that we're going to be doing and the ionic equations that we are writing are all really focusing on the precipitate part. So you'll see that when we get into it. Go ahead and do a level 1 question so far. Definition probably makes the most sense, or list 3 terms related to solubility might be another one. But go ahead and pause the video if you need to write your level 1 question. All right, so let's talk a little bit more about how we show a precipitate. So what we're going to do is we're going to be mixing some ionic solutions. And when you mix an ionic solution, there's really 3 things that can happen. One of them is that, well, nothing new is formed. The 2 things you started with are still there. Well, that's kind of boring. Well, you could also form something new, but everything stays dissolved. So those ions are floating around in the water, but they just are floating around as water ions. That's kind of boring too. The third option is you form a new identity, and that new identity is insoluble. All right, so if we're observing something in a lab and we mixed ionic solutions, how would we know if something was soluble or insoluble? Think about that for a few moments. How would we know? Yeah, the answer is we would see a precipitate if it's insoluble. Soluble means that everything dissolves. So that means that everything stays mixed together like a homogeneous mixture. If we see something chunky or cloudy or floating around after the mixture happens, we know that there's a precipitate. And that is what we are focusing on in today's notes and in our next lab. So we're going to use this information. So how do I know if something is insoluble? Looking for precipitates, mixing different solutions. We can use all of this to answer the lab essential question. And the lab experiment that we're doing is this. Imagine you have a coworker who made a mistake and they spilled a bunch of chemicals in the chemical storeroom. Oh, how annoying. And then they were nervous, and so they ran away and they didn't tell anybody. So you go in there and you see the spill and you're like, wait a second, well, here's a problem. One, now we have this wasted chemical that we have to buy more of. And then also, because of it sitting there for a while, the liquid that it was in, like dissolved or smeared or whatever, you can't see the label anymore. So you've got this unknown chemical spill. Now, because of where it was spilled and the way it looks, you kind of can narrow it down. It's not like it's just, oh, it's any chemical ever, but we want to figure out what that chemical is. We know that we've narrowed it down to 6 different ionic solutions. So what we're trying to answer in the lab is, what is the identity of this unknown chemical spill? So that is our essential question for this lab. So what we're going to do is we're going to take some data, and then we're going to compare that data to data that we take from that chemical that was spilled, that we don't know what the identity is, and we can do matching. It doesn't sound very complicated, but that's a huge part of analytical chemistry and different chemistry experiments and forensics experiments, where you take data of something you know all the details of it, and then you match it to tests of a chemical you don't know, and you can identify that unknown. So that's what we're going to do for this lab. The procedure for this lab is, well, here's the materials you're going to use. You're going to have your 6 different solutions in dropper bottles, and you're going to have the unknown in a dropper bottle. You're going to use something called a well plate. It's a little plastic dish, and these little circles are called wells. They're just little like dividers between these things. So you can mix a couple things here, mix a couple things there. You're going to put about 2 to 3 drops of each solution in one of the wells, and then you're going to, you'll be mixing 2 different solutions at a time. So 2 to 3 drops of the first one, add 2 to 3 drops of the second one. Some of the reactions are slower than others, so you're going to observe your well plate before you clean the whole thing up. The data that you're looking for is did everything stay soluble? Like if you slide this well plate over the top of your lab handout, can you see directly through it? Even if it changed color, like clear and yellow mixed and now it's yellow, but you can see everything through it, then that's still soluble. What we're looking for is I for insoluble. So insoluble, and then you're going to give like 2-3 word description to describe what that insoluble precipitate looked like. So that's the data that we're going to be taking. When you do the lab report, which is actually just going to be the handout for this lab that I give you, the calculation section would come after the data. But you're not really doing math calculations, not those kinds of equations. You're going to do chemistry equations, and they're going to look like this. So you've got one version that's here and a second version that is here. Take a look at these 2 equations, number 1 and number 2. And this would normally be in one big long line. I just ran out of room. So it's not normally 2 different lines like this. It just would be too small if I tried to put it in one line. So what I want you to do right now, yes, out loud by yourself, doesn't matter if there's anyone near you, doesn't matter if you're by yourself, out loud to yourself, compare and contrast these 2 equations. Number 1 and number 2, what do they have that's the same? That's compare. Number 1 and number 2, what do they have that's different? Pause the video and go ahead and just out loud with yourself, compare and contrast. Go ahead, pause the video. All right, so maybe you notice things like, oh, number 1 has way more pieces than number 2. That's a contrast. Number 1 has, well, I guess that's really the big thing. It has extra pieces. They both have this PO4 and this CA. They both have an arrow. They both have this big compound at the end. So that would be compare. Well, these 2 types of equations are what we're learning how to do today. So what we're learning is, what are the equations you write when you mix ionic solutions? One is called the complete ionic equation, and that shows all of the ions that were present in that reaction when you mix the solutions, and also any compounds that might have formed. So ions that are floating around that dissolved in the water, and any compounds or precipitates that also formed. A net ionic equation shows just the ions and compounds specific to that reaction. Kind of like your net income. When you get rid of all of the things that you can't use, the net income is what you have left. The net ionic equation is the stuff we actually used to make that reaction happen. The extra pieces that were floating around, you got rid of them because they are not specific to the reaction that we saw. And you'll see what I mean when I do some examples, but these are just your definitions. All right, ready for a level 2 question? A compare and contrast would be a great example of a level 2. However, you could, of course, use any other sentence starter from your Costa question guide. Pause the video to your level 2 question. Take a little break, go stretch, come back when you're ready. All right, let's continue on. So go ahead and do this with me. This is the reaction that I'm going to use to teach you how to write a complete and net ionic equation. So I'm mixing together calcium sulfide, that's a compound solution, and I'm mixing together potassium phosphate. That's the other solution. So if this was in our lab, I would take 2 to 3 drops of this and put it in the well plate, and then 2 to 3 drops of this and put it in the well plate. And when I did that, I would have seen a precipitate form. It would look cloudy or chalky or chunky or something like that. So because I saw a precipitate, I want to show the chemical reaction in an equation. So we're going to put this just right, keep putting it in your notes because this is an input example that I am giving you. We're going to start by writing out the 4 ions. How do I know there's always going to be 4? Because remember, these are ionic solutions, and ions always are made of a positive and negative. So if I have 2 solutions, I have 2 positives and I have 2 negatives. So there's always 4 ions, no exceptions if you're writing a complete ionic equation. 1, 2, 3, 4. So I look at calcium. So I need the symbol for calcium. It is Ca plus 2 charge because an ion means you're showing the charge. Sulfide. Actually, I don't want to show them to you yet. Let me break it down first. So we did our calcium. Sulfide, remember, means sulfur. Ide endings are elements. So capital S also has a -2 charge. Potassium is K from the periodic table. Look at where it's located on the far left. It loses 1 to be stable, so K has a +1 charge. And phosphate, 8 endings means you're looking on the ion guide sheet. You look it up, PO4 -3 is given. So this is calcium, this is sulfide, this is potassium, this is phosphate. And then I put these little AQs next to them. That's a new notation we haven't seen before. It stands for aqueous. Aqueous means it's mixed with water. So these 4 ions are in solution. We knew that because we always start with an ionic solution mixed with another ionic solution. These AQs tell you that these things don't stay bonded to each other. So calcium and sulfur are not connected. That's also what the plus sign means. So each one of these is an aqueous ion floating around in water. Those are the 4 pieces that are available to make this chemical reaction happen. The next step is decide what goes on the right side of the arrow. And to do that, we're going to switch partners. So the calcium ion used to be with sulfur originally before I mixed it with water, and the potassium ion used to be with phosphate. So when they switch partners, you still have to go opposite charges. So calcium was positive, sulfur was negative, potassium was positive, phosphate was negative. So when calcium switches partners, it's not going to be attracted to potassium because they're both positive. Calcium is going to be attracted to the phosphate. Sulfur will be attracted to the potassium because they have opposite charges. But here's the part that is the new chemistry. 2 of these ions make the precipitate that we saw, and the other 2 ions stay dissolved as ions. So what we're going to do is we're going to figure out what compound was the precipitate, and we're going to put a little S next to it. We're going to put the AQ, because it stayed dissolved, next to anything else. So 2 of these parts are going to make a precipitate, and we're going to put S next to it. The other 2 parts are going to stay as ions, and we put AQ next to those. Again, I'm teaching you lots of new little details, so kind of just write stuff down, process as we go, pause the video if you need to, and then we'll see these as examples, and then you'll practice it. Okay, so the question you might have had is, well, wait, how are we supposed to know what the precipitate is? Well, you have a solubility chart on Schoology where you will find, for example, let me go back for a second. On the solubility chart, you'll find something like calcium and something like potassium on the left side of that chart. And then you'll find something like sulfide and something like phosphate on the upper part of the chart. Like the top row is the anion or the negative pieces. So what we're going to do is we said that calcium would be attracted to phosphate. So we would look at that solubility chart and we would see that calcium, where calcium and phosphate meet on that solubility chart, we would see that that says I for insoluble. Well, insoluble, remember, is a precipitate. If we find potassium and where sulfide meets, so again, on that solubility chart, it's a data table that's on Schoology, you would look for potassium and find sulfide, find where they meet, and you would see that there's an S in that column. So that tells you that the sulfide and the potassium does not make a compound. They stay dissolved. We will put AQ next to them. But I do have a little shortcut I want to tell you. Oh, sorry, I guess I had this here. So again, calcium and phosphate are attracted to each other. We look on the solubility chart and we see that where those 2 things interact on the solubility chart, it says I for insoluble. Potassium and sulfur, when you look at where those 2 things intersect on the solubility chart, you will see that it says S. A hint that I can give you, if you look on the solubility chart and find nitrate across the top and then go all the way down the nitrate column, you'll see that every nitrate is soluble. So if one of these pieces had been a nitrate, we wouldn't even need to use the solubility chart because we would know that the nitrate compound that was trying to be made would always be soluble. And just a clarification, what does soluble mean again? Does that mean it is the precipitate or not the precipitate? Think. Yeah, it means it's not the precipitate. Nitrate compounds will never make a precipitate. So we don't have any known compounds with nitrate that ever are precipitates. They're always soluble. Okay, so we already have our 4 ions. The next question was to decide what goes on the right side of the arrow. So we used our solubility chart. Calcium and phosphate are attracted to each other. They make a precipitate. But look at, that's a +2 and that's a -3. So when they make a precipitate, it's a stable compound. It needs to be neutral. So I have to find a common multiple, which would be 6. I'm going to times this by 3, so I have 3 of them. I'm going to times this by 2, which means I need parentheses and a 2 on the outside. That will be my precipitate. This will stay exactly like it looks right now. This will stay exactly like it looks right now. So I've got my precipitate, which is what the little S stands for, solid precipitate. And then you've got your 2AQ pieces that did not form the precipitate. All right. So notice what I have here. Here's my 4 starting pieces. Where did they come from? Calcium, sulfide, potassium, phosphate. Then a reaction happened. I mixed them together and something new was formed. One of the new things that formed was a solid compound, that's your precipitate, and then there was 2 extra ions still just floating around. So what you have here is this, so what we just did, with the ions switch partners and we place an S next to the compound that made the precipitate and left the other 2 things as ion, this is your complete ionic equation. It shows all of the pieces that are present. 4 ions making 1 precipitate and 2 extra ions. So if you want a little summary, if I ask you to write a complete ionic equation, it will always, no exception, start with 1, 2, 3, 4 split apart ions that are all aqueous, and then it will have an arrow, and then it will make 1 precipitate only and 2 extra ions. Because remember, 2 of these ions form the compound, and then there's 2 leftover pieces. This is the definition of a complete ionic equation. It's showing the chemistry that happened instead of just saying, oh, there's a precipitate. Now you're actually showing the chemistry. That's the new level that we're learning today. All right. So again, this is your shortcut. Complete because it shows all the parts, and it always goes 4, arrow 3. 1, 2, 3, 4, arrow, 1, 2, 3. So you can use that as kind of a summary to help you check your work. Okay, the next piece of this is, well, what about the net ionic equation? So you have your complete ionic equation. You've done all the hard work. Now what we need to do is, if we want to show the net, we want to show the stuff that is specific to this equation. So we're going to cancel the spectator ions. Now think about it. A spectator is if you're at like a volleyball game or a basketball game, the spectators are in the stands. They're just watching. They're not making the work happen. So in a complete ionic equation, the spectators are the ones that are not making the reaction happen. So for example, it doesn't matter that this is sulfur and this is potassium. All that matters is that you have calcium and you have phosphate. So that means that those spectators don't matter. So the sulfur and the potassium did not make the precipitate. The potassium and the sulfur at the end are just staying dissolved. So cancel out the spectators, the ones that did not make the precipitate. That's what a spectator is. Why is it a spectator? Because it's not specific to this reaction. This game would keep happening no matter who was sitting in the stands, right? This precipitate would happen no matter what these 2 pieces were. So if this had been chlorine instead of sulfur or oxygen instead of sulfur, it's the calcium that matters. This could have been barium or magnesium, any other positive piece that was attached to the phosphate. It's the phosphate that matters. Rewrite what you are left with. Calcium ion, phosphate ion, arrow, precipitate. That is your net ionic equation. So it's kind of like the summary of what matters in this reaction between these ions to make this precipitate. These spectators don't affect the precipitate. So this is like the summary of the chemical reaction. Some calcium and some phosphate specifically make this precipitate. And the reason it's the net ionic equation, it shows the parts that are left when you get rid of the spectators. So it's always 2 ions, arrow, 1 compound. 2 ions, an arrow, and one compound. That will, again, there's no wiggle room with that. So when you're trying to check your work, if I ask you for a net ionic equation, you better start with two ions, meaning they need to have their charges. Then you have an arrow, and then you have a stable compound. So no charges, it's neutral now. All right, so the purpose of the net ionic equation is to show the ions that came out of the solution to form the precipitate. All right, go into your level 3 kind of question. Look at your COSTA guide if you need to for some different sentence starters. But that is how we do a complete and net ionic equation. So I'm building on your chemistry knowledge to now get a little bit more specific about how we represent a precipitate. Now that we know about how to write formulas and we know about ions, we can do something like this. All right, so to practice this, there is an ionic equations practice assignment on Schoology. There's 2 examples, but you're going to show me 4 equations. You're going to do this should say complete, not compete. Complete and net ionic equations for number 1, and then the complete and net ionic equation for number 2. So it's 2 problems, but total when you're done with the assignment, you should have shown me 4 ionic equations, complete and net for both of them. Okay, now before we're done with our notes technically, but before I let you go, I want to talk just a little bit more about the lab. So the lab essential question is, what is the identity of that unknown lab chemical that spilled? And remember, the idea is that we're going to test a bunch of known chemicals, and then we'll test the unknown, and we'll match the results to make our prediction of the unknown lab chemical. When you do the lab report calculations, you're going to choose 3 pairs of solutions that made a precipitate. So the ones that were soluble, we don't care about those because there's no chemical reaction to show. For each of those 3 pairs of solutions that made a precipitate, you're going to figure out what the precipitate is. Remember, you're looking on that solubility chart. You're going to write just the net ionic equation and the name of the precipitate. So what this lab is going to show me is, do you know how to write ionic equations? Do you know how to do chemical names? And then also, of course, because you're doing equations, you'll also be showing me chemical formulas. This lab is actually the assessment for this unit. There's no separate quiz. So that's why it's important that you do this calculation section accurately, because this is how you're going to show me that you understand formulas and names and equations. All right. So this handout that you'll use later this week, this handout will be your lab report. You won't have to start from scratch and write a new lab report just for this lab. All right, in your CER conclusion, your claim is going to be what's the identity of the unknown. The evidence will give me specific observations from your data table. So don't just say, oh, because the data matched. That's not evidence. That's just another claim. So if you say, oh, the identity of the unknown is copper 2 nitrate, your evidence needs to say, because when I mix the unknown with this chemical, I got a cloudy yellow. And when I mixed with the copper 2 nitrate, I got a cloudy yellow. So a few specific observations from the data table to support your claim. This evidence won't look like measurements. It will look like specific observations. And then the reasoning for this lab is, what's the chemistry that happened so that you can get the evidence? So hint, you should be talking about things like a chemical change. What is a precipitate? What does it mean to be soluble or insoluble? Those are the chemistry concepts that you explain. Don't just list them. The reasoning is where you explain things. What's the chemistry that happened to help me understand these soluble and insoluble and precipitate compounds? The timeline, the lab will be assigned on January 13th. That's for all classes. And the report will be due by January 19th. That's for all classes. There's no school on January 18th, just so you know. So this is true no matter what hour you have from me if you're in my current class this trimester. All right, that brings us to the end of our notes and our pre-lab, the end of Unit 2, Day 6. So if you didn't do so already, go back and finish your COSTA questions and then write your summary for the first EQ that we went through today. How do I write net and complete ionic equations? And then you're going to work on that ionic equations assignment. It's due on Wednesday, which means that we don't have a Zoom session before this is due. So make sure you use my office hours if you have any questions. You could always work with other people. Like if you have a friend in my pre-AP Chem class, you could work with them safely, obviously. But if you do have questions, make sure you check in before Wednesday or on Wednesday, because that's when that assignment is due. All right. Thank you for all of your focus today. So our next Zoom session will be your lab. So there won't be any video notes or anything. You'll just watch the lab video, take data, and then do the lab handout as the report. Remember that lab handout report is due January 19th. Thanks so much for listening as we continue to build our knowledge of chemistry. See you next time.